Today we are beginning circular motion, and we begin circular motion by talking about centripetal acceleration. And one of the tricky things about centripetal acceleration is a lot of time we're talking about going at constant speed, which brings up the question, how can you accelerate while you're going at constant speed? So some things you need to remember. Acceleration is your change in velocity, so you need to remember that. Velocity is a vector, which means it has magnitude and direction. And so if we're going in a circle, we are changing direction. And if we're changing direction, we're changing our velocity, therefore our velocity is changing. And if our velocity is changing, we are accelerating. And that acceleration is our centripetal acceleration. So we're moving in our circle, and we were traveling this direction. And if we continued to travel that direction, we would just go straight. So something is pushing us this way. We'll go into that in the next chapter, but we're going straight. We're getting pushed toward the center of the circle. We're going this way, and we're getting pushed toward the center of the circle. And that acceleration towards the center of the circle is what's known as our centripetal acceleration. We'll go into the force that provides that acceleration in the next video. But for right now, we need to know that the equation for centripetal acceleration is v squared over r, where v is the speed that we're going, because remember we're changing direction, so it's not really a velocity. The speed that we're going divided by the radius of the circle. So what does this equation tells us? Since we have v squared on the top, that means that the acceleration is proportional to the square of our velocity. If we take that velocity or that speed and double it, we need to square it, so we're going to end up with 4 times the acceleration. If we tripled it, we would have 9 times the acceleration. And since r is on the bottom, if you're going to divide by a small number, basically what's going to happen is you're not making this as, you're making it a big number. So if we divide by like 0.001, our acceleration is going to be really large. If we divide by like 50, then our acceleration is going to be really small. And, depending on your application, it's good to have a small acceleration or it's good to have a large acceleration. So basically, our centripetal acceleration will increase as our radius decreases, and that's inversely proportional. So centripetal acceleration and the radius are inversely proportional. So let's solve a couple sample problems. We have the equation centripetal acceleration is equal to v squared over r. So let's read our problem. What centripetal acceleration, so that's what we're looking for, is experienced by a 1,000 kilogram car, so that must be its mass, traveling at 20 meters per second, so that's its speed, around a turn with a radius of 50 meters. Well, see, mass isn't anywhere in our equation, is it? There's no mass in our equation, so we don't need the mass. The mass is kind of just in there to throw us off a little bit. But we put everything in the equation. AC is equal to 20 squared divided by 50. So it's equal to 400 divided by 50. So it is 80, or 8 meters per second squared. Since it is an acceleration, it has the same units as acceleration, so it's meters per second squared. Okay, so here's sample problem number 2. If the space station rotates at a speed of 10 meters per second, so that's our speed, what would its radius have to be? So that's what we're looking for, so that the astronaut would experience 1g. 1g is 1 times the acceleration due to gravity, which is 9.8 meters per second squared. So our acceleration, our centripetal acceleration, is 9.8 meters per second squared. So plugging it all in, we have a 9.8 for our acceleration. We have 10 meters per second for our velocity. Don't forget to square that. Then we have r on the bottom. So we have 9.8 equals 100 over r. Now here's where we often commonly make mistakes. And so when the problem is that our variables on the bottom, we're very tempted just to divide by 100, and that it's going to leave us with 1 over r. So if we put this over 1, now it's pretty obvious when we look at this that what we have is a proportion. And so we'll cross multiply and divide. So we get 100 is equal to 9.8 r, and r is equal to about 10.2 meters, which isn't huge. It would have to have a radius of 10 meters, which would mean it would have to have a diameter of about 20 meters. So the space station doesn't need to rotate as fast as 10 meters per second in order to give us 1g of gravity. Final problem. This one should be a little bit easier. How fast will a car go around? So we're looking for v. A 30-meter turn, so that's our r. In order to experience a centripetal acceleration of 5 meters per second squared. So putting it into our equation, v squared over r, 5 is equal to v squared over 30. V squared equals 150, and again, common error, forgetting to square root, so we're going to take the square root of both sides, and we get v equals 12.2 meters per second. And that does it for centripetal acceleration. Our next video is going to be on centripetal force. So go ahead and move on to that one. Good luck.